Hello, my name is Stephen Morris from the University of Toronto, Department of Physics. This talk is called That Warm Feeling, the Evolution of Electronic Design from Tubes to Nanotechnology. It's part of a series called DX Physics, which is a partnership between the Department of Physics and the Design Exchange in Toronto. This particular talk is part of an exhibition at the Design Exchange called The Art of Clairtone, the Making of a Design Icon. I'm going to hit various themes today related to electronics and how it impacts design, how audio devices have evolved over time to use different kinds of physics in their design, and especially about how electronics has transformed not only the way we live, but also the way we listen to sound. Here's a picture of a famous stereo made by Clairtone in the 60s called the Project G. It was the first hi-fi device to have external speakers symmetrically on both sides, a very influential design. And I should say that a lot of the pictures I'm going to show in this talk were provided to me by D.C. Hillier, who has refurbished many Clairtone machines for the exhibition at the Design Exchange. No technology in the history of humanity has evolved so radically and so transformatively as electronics. So let's look at a brief history of electronics. It all goes back to Thomas Edison and the light bulb. Everybody knows the story of how Edison invented the light bulb by basically trying everything. Well, one day, among other things, he tried a filament inside of an evacuated bulb with no air in it at all, and he discovered something called the Edison effect. If you attach a small plate to one side of the electrodes of the light bulb, you discover that the current will pass through the bulb in one direction, but not in the other. And it was a physicist named John Ambrose Fleming who studied this effect, which he called the Edison effect. And eventually, this led to the invention of the vacuum tube. In effect, Edison had accidentally invented a vacuum tube diode, which is a device I'll describe in a little while. Fleming and De Forest in the early years of the 20th century perfected this, and here is a picture of what I would call a late tube. This is a tube that you might find in a stereo or a television built in the 50s or early 60s. And that led to audio devices that used tubes, which persisted until about the early 60s. Tubes were used in televisions for much longer than that. And then, of course, the next development was the invention of the transistor. Unlike Fleming and De Forest, who were basically lone inventors, the transistor was invented as a result of a very definite large-scale research operation by a large company, the Bell Telephone Laboratories. And it was invented by Shockley, Bardeen, and Brattain in 1947. But they discovered that when they went to patent this device, that it had actually, a version of the transistor had in fact been patented already in Canada in 1925. So that made the patent history of the transistor very complicated. Eventually, Bardeen and Brattain got a patent on something called a point contact transistor, and Shockley obtained a patent on a different semiconductor device. But originally, transistors were individual, discrete elements which were packaged in little metal cans like the one you see there with 3 contacts on them. And eventually, as part of a program to try to figure out how to manufacture transistors more efficiently, the integrated circuit was invented in the late 50s and early 60s. And the original idea was to print many transistors on a very small circuit and cut them apart and just use that as a way of manufacturing discrete transistors efficiently. And it was eventually realized that all the other components of the circuit could be made out of semiconductors as well, and they could all be interconnected on the same piece of silicon, and that led to the invention of the integrated circuit. Now, the integrated circuit didn't really take off until about the 1970s or so. And of course, there are both digital and analog integrated circuits, although we typically think of digital circuits today. Now, the Clairtone company was started in 1958, and it began by making tube devices. And in the about 1963 or so, they became early adopters of the discrete transistor. And it's interesting that they managed to go broke just as the integrated circuit was getting started. So Clairtone hi-fis or stereos occupy an interesting niche in the history of electronics, somewhere between the late tube era and the beginnings of the integrated circuit era. So let's go back to about the 1930s and look at how things were designed in those days. And what could be more comforting than a cathedral-shaped radio? It's very symmetric and pleasant wood grain color. And you can, of course, imagine listening to, say, a fireside chat by Roosevelt on a radio like this. And of course, it does get warm during its operation. If we take apart the radio and look at the back, you'll see it has a classic tube design. There's a metal box at the bottom which contains all the other components. The tubes and other things are fitted into sockets on top of that box. And you can see that some of the tubes really do look like light bulbs. So in the early 60s, late 50s and early 60s, Clairtone was making tube stereos using a design similar to this. And they were packaged in these beautiful pieces of cabinetry, kind of classic wood pieces of furniture. And they used tubes that look like this. Here are some actual tubes from Clairtone's designs. Tubes always have this wonderful naming convention, the 6BA6, the 12AX7A, and so on. And people, tube enthusiasts, get quite romantic about these things. The 12AX7A, for example, has its own Wikipedia page, and it's beloved of music lovers around the world. It's found in guitar amplifiers and many other things. And so people get quite nostalgic for these names. But you see, these tubes look a little different than the one from the old Philco radio. They're a lot smaller. They typically don't have bases that are molded out of a single piece of glass. The 50L6 is a higher power tube, which is why it has that black jacket on it like that. The most basic part of an audio device is the amplifier. And the essential idea of an amplifier is to take a very small signal and use it to modulate the dumb power supply and to produce a larger signal that can be used to drive a speaker. The small signal can come from anything like a radio tuner, a microphone, a guitar, electric guitar, a phono cartridge. The phono cartridge is, in case you don't remember, is the little device at the end of the tone arm that converts the mechanical movement of the needle into a very small electrical signal, and that signal has to be amplified. So let's look at how a vacuum tube works and how it does this. This is how the Edison effect works. First, you start with a volume from which you take out all the air. That makes a vacuum. And then you put a filament in that volume, something like a light bulb. And when you light up that filament and use that to heat up a metal electrode, what happens is the electrons in that piece of metal, and pieces of metal have plenty of mobile electrons in them, which are represented by the little blue dots in this picture. When you heat up that piece of metal, the electrons actually boil out of the metal and are found freely roaming around in the empty space around the outside. That's called thermionic emission. Now, to complete the tube, we put a plate on the other side, and if we apply a large voltage between the hot electrode, which is called the cathode, and the plate, making the cathode negative and the plate positive, then what happens is the electrons, which are negatively charged particles, are attracted to the plate, and they freely fly across the vacuum and close the circuit. So this, we say that in this case that the tube is conducting. If, however, I reverse the polarity of the voltage, I put the positive voltage on the hot electrode and a negative voltage on the plate, Then what happens is the electrons are attracted, those that boil off, or simply attracted back to the hot electrode, and none of them stream across the gap. And so the tube does not conduct in this direction. And this is the Edison effect. This dependence on direction of the polarity of the voltage makes this device a rectifier or a diode. So it only conducts electricity in one direction when the hot electrode is made negative and the plate is made positive. Now, to turn this into an amplifier, Fleming and De Forest invented the idea of adding a grid, an extra electrode in the middle, in the shape of a little grid made of mesh. Now, if I apply large positive voltage to the plate and a medium positive voltage to the grid, what happens is the electrons happily boil off the negative electrode, are attracted to the grid, pass right through it. Some of them are attached to the grid, but most of them keep going and are attracted to the positive plate, and the tube conducts. On the other hand, if I put a small negative voltage on the grid, then what happens is the electrodes that would like to stream across are just repelled back to the electrode from which they came, and the small negative voltage on the grid effectively shuts off the flow of electrons between the negative electrode and the plate. So the small voltage that we apply to the grid can control a much larger current passing between the two electrodes. So this is the elements of an amplifier, because I can use the small signal on the grid to control a much larger signal passing between the other two electrodes. So here's a simplification of an amplifier using this principle. See, that's the symbol for a tube in the middle there. The orange thing is the filament that keeps the electrode hot. And you see the signal is brought in on the left and passes through a capacitor and is applied to the grid of the tube. And the power supply is applied between the two electrodes. And effectively, the input modulates the much larger power of the power supply and produces the output, which is much larger. That makes it an amplifier. So here is a schematic of a small part of the tube Clairtone amplifier, which was used in several different models of the Clairtone series in the 50s and early 60s. And if you look closely in the yellow box, you'll see there is a 12AX7A there, which is wired exactly as I've described. The signal comes in from the left, is applied to the grid, and it modulates the voltage between the electrode and the plate. And if you follow the lines, that leads to the grid of the next tube, and so on. So it's a staged amplifier. Each tube does a little bit of work to increase the power of the signal, and eventually it makes it over to the right-hand side, where those objects in the red boxes are the speakers. This is a stereo amplifier, so that there's a complete duplication of the two sides. The top part of the diagram is the left channel, and the bottom is the right channel. In fact, the 12AX7 has not one, but two separate triode amplifying devices in it, inside the same glass envelope. So the one at the top is one part of the same tube, the one at the bottom is the other part of the same tube. Now, I don't have a picture of the inside of an actual Clairtone tube amplifier to show you, but I have another device which is very similar in its construction. This is the little signal generator that I have in my collection. Here's what it looks like from the outside with the back taken off. You can see there are a bunch of devices and a few tubes mounted on top of a box. If you look inside the box, this is the sort of construction that was used. The orange things are capacitors, and there's resistors with stripes on them, and those large black things are the bottoms of the tube sockets. So you'll notice that there isn't any printed circuit board used. In fact, printed circuit boards were hardly ever used for tube devices. Instead, the inside of the box was typically a kind of rat's nest of wires like you see, with all the components soldered between the tube sockets, and maybe occasionally a separate junction bar. This kind of device would have been soldered together by hand by factory workers. Now, some characteristics of this type of tube device are it's a completely open design. Everything about this device is given to you when you buy it. In fact, every Clairtone stereo came with an extensive manual, not only with a schematic diagram, but with a complete map of where to find every component. And of course, tubes have filaments, and just like light bulbs, they break. And it was expected that you would be able to service this device yourself. So here's a device that we used to see in hardware stores all the time. It's a tube tester. You would go and pull the tubes out of your stereo, take them to the hardware store, stick them in this device, look up which tube it was, set some dials, and it would simply tell you whether the tube was good or not. You could often fix one of these things by just turning it on and looking in the back and seeing which tubes lit up and which ones didn't. Another feature of all of these things, of course, was that they used analog controls. The volume, the tuning knobs, all move smoothly in your hand. Here's a picture of a tuning capacitor, which you would find in the back of any old radio or stereo. A capacitor is a device whose function depends on the overlap between two plates, how much area they overlap by. So as you turn the knob to tune between different stations, what you're actually doing is leafing together and unleafing these many little plates. And so this gives you a very tactile sensation. It gives you a smooth feeling of continuous control. As I've shown you, all the parts inside of these devices are at the human scale. There's only a few tubes in any, even a rather high quality device like a Claretone stereo, there'd only be perhaps 6 or 8 or 10 tubes. And of course, when it's in operation, the whole thing warms up and gives you that warm feeling. So just to show you that tubes were not completely clunky, here's an amazing application of tube technology from 1943. Here's a little circuit diagram showing a 4-tube device. And this device, believe it or not, fit into the nose of an artillery shell. It's called a proximity fuse. And how it worked was it produced a little radio signal which came out the side of the shell. And as the shell spun toward the aircraft that was its target, any reflection off of a metal object in the nearby would trigger the thing, and it would detonate the shell. In order to make a tube that survived the incredible acceleration of being fired out of a cannon, a special tube, very robust miniaturized tube was required. And here's a diagram of that tube. You see it has a very thick wall, and 4 of these devices were used in the shell. Well, tubes didn't last forever. Here's a 12AX7, and as I mentioned before, around the late 50s, early 60s, there was a transition to the transistor. And this is what the first transistor looked like. It's a clunky looking laboratory device, but eventually it was replaced by a very small, low-powered discrete component with 3 contacts, whose relative size of the tube was about as I'm showing here. In order to understand how a transistor works, we need to talk a little bit about a semiconductor. It turns out if you take a piece of ordinary silicon and add a few tiny fraction of impurity to it, you can make what's called N-type silicon. N-type silicon is a kind of weak metal. It has a few free electrons, here shown as blue dots, in it. And if I apply a voltage between the two sides of this little piece of semiconductor, what happens is, rather unsurprising, the electrons move and the semiconductor conducts electricity, something like a weak metal. That's why it's called a semiconductor. And it conducts electricity because the electrons move. Slightly more surprising things happens if you take pure silicon and dope it with a slightly different other chemical. Then you find that in place of the electrons, you can actually make holes, or the absence of electrons. And this is called P-type silicon. The best analogy I can make here is if you have a highway with cars on it, with just a few cars, and those cars are like the electrons in the previous picture. If you crowd the highway up so that it's completely full except for a few spaces the size of a car, then you can think of those spaces as moving around, and those are like the holes in P-type silicon. So if I apply a voltage to P-type silicon, it conducts electricity, but now it's really the holes that carry the current, and the holes are positively charged. They act like positively charged particles, so they move away from the positive electrode and toward the negative one. Now, to make a diode or a rectifier or a device that conducts electricity in only one direction, it suffices to make a junction between N-type and P-type silicon. Now, if I apply a voltage in this direction, what happens is the electrons happily move from left to right, and the holes from the P-type happily move from right to left. And when they meet together in the middle, they annihilate each other. But more holes are made at the positive electrode, and more electrons are made at the negative electrode, so the current keeps flowing. And in fact, in certain special materials, every time the hole meets an electron and annihilates, it releases a little bit of light, and hence that makes what's called a light-emitting diode. If I reverse the voltage on a diode, then the holes are attracted to the negative electrode, the electrons are attracted to the positive electrode, and that leaves nothing to carry the current in the middle of the device. The junction area becomes depleted of charge carriers, and no current can flow. So in this direction, the current through the device is blocked. So in this way, it behaves a bit like the diode tube that I showed you a little while ago. It conducts electricity one way, but not the other. Now, to make a transistor, what we do is we sandwich a small slice of P-type silicon between two slices of N-type silicon. And then we attach a third electrode to that thin slice, which is called the base. Now if I apply no signal to the base, then what happens is that the electrons cannot get through the P-type region, and that acts as a barrier, or something like the plate did in the tube, and so no current flows. If, on the other hand, I apply a signal to the base, that is to say I make the base more positive, then what happens is holes are injected at the base. They annihilate with some of the electrons that are coming from the negative electrode on the left, which is called the emitter, and that actually clears the way for most of the electrons from the emitter to flow happily through the base toward the collector on the other side, which is positively charged. And so, again, a small signal applied to the base controls a much larger signal of electrons, in this case, flowing from the emitter to the collector. So the base acts a little bit like the plate, or like the grid in the tube I described earlier. Now this is called an NPN transistor. It's also called a bipolar transistor because it contains charges of both kinds. So to make that transistor into an amplifier, it looks something like the amplifier I showed you before. The signal comes in at the left and is applied to the base, and that small signal modulates the much larger current being supplied by the power supply between the emitter and the collector. And that gives you a larger output on the right-hand side, an amplified output. Here's a schematic from, a small part of a schematic from the Clairtone T313 amplifier. And if you look closely, you see here is a NPN transistor wired exactly as I've described. The signal comes in from the antenna actually on the left and is applied to the base of a transistor, and the signal from that transistor is passed to another transistor and so on. The Clairtone T313 amplifier contains about a dozen transistors. Here's what it looks like if you were to take it apart. It's very complicated in its construction. It contains sometimes both circuit boards and the wiring scheme that I described before it was used for tube devices. you can see lots and lots of parts and lots of wires. Here's an example of a small radio that uses a printed circuit board. This is a relatively simple radio. It only has a few transistors. The black objects are the transistors. The other things are resistors, capacitors, coils, and so on. If I turn it over, you see how they're wired. Each one has little legs which poke through the insulating printed circuit board and are soldered together on the other side using a lot of solder. And there's still a lot of wires. Well, somewhere around the 1980s or so, analog gave way to digital. How does that work? Well, an analog signal is something like this. The voltage being applied, say, to the speakers is just proportional to the amount of loudness you'd like to produce, or to the deflection of the needle on the phonograph. How digital works is it very quickly measures the size of that voltage and records it as a pure number, which can be recorded in binary form. So the digital signal can be recorded much like any computer file and reconstructed by something called a digital to analog device, which simply produces a voltage proportional to a number which it's given and does it very fast. So once we made the transition between analog devices and digital ones, sound reproduction really became a kind of computer problem. And the one thing we know about computers is that they get faster and faster with time. About the time that Clairtone went broke in the 1970 or so, the first integrated circuits had a few thousand components on them. Then something truly remarkable happened, which has come down to us as Moore's Law. Gordon Moore wrote an article in 1965 in which he predicted that transistors and the circuits that they were made into would get smaller and smaller and faster and cheaper and cheaper. And this has proved to be true for many years. On this graph, we have a vertical scale which goes up by a factor of 10 for each line. So starting around 1970 with a few thousand components, by the mid-80s we had hundreds of thousands of components, hundreds of thousands of transistors, then tens of thousands, then hundreds of millions, and finally around now we have transistor devices using more than 1 billion transistors. The chips themselves are about the same size, and the transistors just keep getting smaller and smaller. The current generation uses devices which are 45 nanometers across. And here's a scanning electron microscope picture through a modern chip, and you can see a little bar at the bottom which shows 100 nanometers. Now, a nanometer is a very difficult thing to think about. It's a millionth of a millimeter. There's every reason to think that this process will continue for at least a few more years. Here is a picture of a recently published device which is said to be the smallest transistor ever made. It's a single transistor which is only 20 nanometers across and only a few atoms thick. For reference, an atom is about 1/10 of a nanometer across. So a nanometer is about 10 atoms. So modern transistors have only a few hundred atoms, or only a few hundred atoms across. Clearly this can't continue. We can't make a transistor out of a single atom, but we can still continue until perhaps 10 nanometer devices. To contrast the Clairtone stereos that I've shown you, it's interesting to look at a kind of modern cool device, which is the iPhone. This, of course, does a lot more than play music, but to give you some idea of how such a thing is constructed, we can show you what the inside of an iPhone looks like. The black things are integrated circuits, and there are really rather few of them. It uses what's called surface mount technology. Each integrated circuit is mounted directly onto the circuit board, and there's two sides, and the two sides communicate through the little yellow dots. There's very little solder and almost no wires at all. Inside each of those integrated circuits are hundreds of thousands, perhaps hundreds of millions of transistors, which do the very complicated digital things that the iPhone does. Some of the characteristics of this kind of device are, of course, it has no analog controls. The iPhone only has one button. Everything is done by a touch screen. Contains no moving parts. You get no direct tactile feedback about what the device is doing. I think you'll agree that the parts inside these things are not at the human scale. Here's a picture of the Intel Xeon processor. It's a dual-core processor running billions of times per second, and it contains almost 1 billion transistors, 800 million transistors. What's not generally appreciated is that most of these types of devices are not really designed directly by people. They're designed with massive software help. All of the layouts of chips in the iPhone are put together with software tools, really. So no human being really knows what each transistor or even what each group of transistors is doing exactly. They're designed and positioned by software. Furthermore, the chips themselves are built in fabrication plants almost entirely robotically. The Intel processor plant in California is about the size of a football field, cost $1 billion, and contains absolutely no human beings. They're much too dirty to have inside of a clean room that's making highly integrated circuits like the Intel Xeon. The design of these sort of devices is extremely closed. Those chips that are, for example, in the iPhone are not something that anyone but Apple can buy. Even if I were to saw one open, it would be very difficult to tell what its function was. You do not receive a complete circuit diagram when you buy an iPhone. And of course, as everyone knows, they're completely unserviceable. They really only fail catastrophically. They suddenly stop working. And there's really no way and no point in trying to repair them. That's not to say that tubes are dead. In fact, there's quite a healthy market for tubes in the audio device world. And it's always said that tubes produce a warmer sound than transistors. And if you want to have an argument between an engineer who understands electronics and a musician who understands music, then get them to argue about whether tubes sound better than transistors. Here's a recently marketed high-end audio amplifier, and unlike the amps I showed you before, this one has all of its tubes prominently displayed because they want you to see those tubes. And I think a very important part of our appreciation of these kind of things is to see the tubes and feel the warmth from them. It's also true that the kind of music that people would like to listen to or play on these devices is very much tied to the distortion that the tubes introduce. So on the right is a Marshall amplifier you can buy. It's an electric guitar amplifier. You can buy it today, but it's an exact replica of the amplifiers that Marshall was making in the 1960s. In fact, it is even model 1960. It uses all the same tubes and all the same designs, right down to the color scheme of the original 1960 amplifier. Tubes still have their revenge, however, or transistors have their revenge. It's possible to digitize the input to an amplifier and in software distort it systematically so that it sounds like any tube device you like, and then put it out again. Here's a little device called a pod, which has a little screen on the front, allows you to select between any different tube amplifier you'd like the device to sound like. And using massive computational power, this device simulates the sound of an old-fashioned amplifier with only a few tubes. Now, of course, we can always have the best of both worlds. And here's a kind of tongue-in-cheek device called iTube, made by an amusing company called Fat Man. You can see that it has a socket for a iPod on the right, and it delivers the digitally stored music to a tube amplifier that you can see with all sorts of nice warm tubes. So it's really gives you the best of both worlds. I like to think that we've actually entered time of post-technological design. Essentially, the technology of electronics is so versatile, we can have it any way we want. We can have transistors where they're appropriate, tubes where they're appropriate, and capitalize on our fondness for tube sound. Thanks for listening.